Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And with this in mind, we're going to look at one of the key practicals that you have to do in A-Level Chemistry, and that is the iodine clock. So we're going to look a little bit about how it works, some of the background information, and how to do the calculations in order to work out an order of reaction with respect to the hydrogen peroxide. So we're going to be focusing this video entirely on the iodine clock. If you find the video helpful, remember to like, subscribe, share with your friends, keep checking back for more content. Okay, so when you've got the iodine clock reaction, you've got two key things in there. You've got potassium iodide, Ki, which is effectively a source of I-, and you're reacting it with hydrogen peroxide, H2O2, and the potassium iodide is causing the hydrogen peroxide to decompose. So you would expect the iodide to form iodine, which is what will give it this lovely colour when it reacts with the starch indicator. But what you also have in your test tube is sodium thiosulfate, S2O3 2-. And what will happen is this sodium thiosulfate, the S2O3 2-, reacts with the iodine before it has time to give it this colour. And then eventually, once all of this sodium thiosulfate has been used up, that's when you see the big blue colour of the iodine, the dark blue. Blue-black is the best way to describe it. Blue-black colour of the iodine. And what you do is you mix the chemicals together, you get your stopwatch out, and you time how long it takes for this colour change to happen. Okay, so what we're going to do here is go through the equations for how this works. So we said that you have potassium iodide, which is effectively I-, and the iodide gets oxidized to form iodine. So you'd need two lots of I-, and therefore this process releases 2 electrons. And the hydrogen peroxide, H2O2, decomposes to form water. Now we need to balance this as a redox equation, so you'd need 2 lots of the water to balance the oxygens. You would then need 2 lots of H+ on this side to balance the hydrogens, and therefore 2 electrons. Okay. And then what we need to do is we cancel the electrons, because you've got 2 on each side, and that gives us an overall equation of 2 lots of I- plus 2H plus H2O2 goes to iodine and 2 lots of water. And a useful thing at this stage is to just go through and count all the atoms on both sides and check that it balances. So you've got 2 iodines here, 2 iodines here. You've got 1, 2, 3, 4 hydrogens on this side, 4 hydrogens here, and 2 oxygens here and 2 oxygens here. So I'm happy that it's balanced. And in terms of charge, I've got 2- here and 2+ here, which gives you nothing, neutral. And this is neutral on this side. So I'm happy that that balances. And then in the next equation, the iodine that is produced from the first step gets reduced back down to iodide again. So that's your first half equation, so you'd need 2 electrons on this side. But the iodine is reacting with the thiosulfate, which is S2O3 2-. So you've got sodium thiosulfate in there. And the sodium thiosulfate reacts to form S4O6 2-. So you'd need 2 lots of thiosulfate. To balance this, you've got a 4- charge on this side and only a 2- over here, so you'd have to have 2 electrons on this side as well. And now we're in a position where we can cancel out the electrons again and combine the 2 equations. So you'd have overall iodine plus 2 lots of the thiosulfate goes to 2 lots of I minus and S4O6 2 minus. And that explains why at first you don't see the colour of the iodine, because it's reacting with all of this thiosulfate, and once this has been used up, that's when you see the colour, and that's when you'd stop your stopwatch. So that's a little bit of the theory behind how the iodine clock works. What we'll do now is look at a bit of data and see how we process it. Okay, so here there's quite a lot of data all at once on the screen. Let me talk you through it. The reaction was done 5 times, hence why we've got flasks 1, 2, 3, 4, 5. And you effectively can think of this as 2 separate flasks. So if I draw a sort of dividing line here, you've got the first section, which has sulfuric acid, sodium thiosulfate and potassium iodide, and you'll notice that everything there is being kept constant. You've got the same volumes of each. So in one beaker you'd have sulfuric acid, sodium thiosulfate and potassium iodide, and then in a second beaker you'd have water with hydrogen peroxide. And the purpose of this is that we're diluting down the hydrogen peroxide, so each time it's a different concentration. So in the first flask there was 4 of water, 1 of peroxide, then 3, 2 and so on. So effectively what we're doing is we're changing the concentration. If the original concentration of the peroxide was 0.1, we can work out what all of the other concentrations would be. Okay. So once you've made up all your different solutions, you would mix the first flask, let's call this flask number 1, and flask number 2. And you'd mix them together and you time how long it takes for that lovely blue-black colour to appear. So when the concentration is low, the time is very high, about 100 seconds. Through to when the concentration is very high, then the time is very low, because you're timing how long it takes for that colour to appear. And it is a sudden colour change. To convert from time into rate, we'd say that rate equals 1 over time. So whatever the value is in seconds, you do 1 divided by the time gives you the rate. So therefore if time is in seconds, rate would be in seconds to the minus 1, because it's 1 over it. And at this stage what we generate is concentration and rate, and we're ready to plot a graph. So at this stage you're ready to plot your data as a graph. The concentration is the thing that you are changing, so it goes on the x-axis, because that's the thing that you're changing. The thing that you're measuring goes on the y-axis. So concentration would be measured in moles per decimeter cubed, and rate in this case is measured in seconds to the minus 1. And then you plot your data as little crosses. This data is fictitious data. It wasn't actually obtained from an experiment. I just generated it to give some nice data. Okay, so, and then at this stage what you would do is you would plot a line of best fit. Now you'd need a ruler for this, because this is a nice straight line. I haven't got a ruler to hand here, so this is my best attempt at a line of best fit without a ruler. But you can see there it's a straight, it should be a straight line of best fit. Line of best fit. And what that tells you, if you were to draw some conclusions on this, is that rate is directly proportional to concentration. And when rate is directly proportional to concentration, what that means is it's first order with respect to the hydrogen peroxide. So we could say here it's first order with respect to the hydrogen peroxide. And then technically, if you wanted to go and work out the rate equation for this, what you would do is you'd go through and say, right, I'm not going to change the peroxide this time, I'm going to keep that constant. I'm going to change the concentration of the potassium iodide, keeping everything else constant. Or I'm going to change the concentration of the sodium thiosulfate. And you could work through these one by one and generate the rate equation Okay, but the logic is we change one thing at a time. And then in true Blue Peter style, here's one I prepared earlier from it. You can see it's a nice straight line based on that data, but it would be a line of best fit for this experiment. Okay, so that's how we deal with data from the iodine clock. Anyway, thank you for taking the time to watch this video. If it's been helpful, remember to like, subscribe, please share with your friends. Keep checking back for more content which is being added regularly. Thanks everyone, see you next time.